Hello and welcome back to my YouTube channel. My name is Professor Kavala, and today I'm going to be talking to you about two Miller effect examples where I previously did a video called What is the Miller effect? And I will post the link on the right hand side of this video. So please check that out before watching this video. And essentially, I'm going to be doing these two examples here and here. And we want to discuss three things, right? So in terms of a question, we want to talk about the capacitors that we can get rid of. We want to talk about the capacitors that we can merge together. And we want to talk about the capacitors that experiences Miller's multiplication to simplify the circuit. All right. If you want to pause the video and see if you can figure these three things out and come back to the video, that would be great. Otherwise, you can follow along and see how we solve these two circuits. But before we dive in, we want to consider where these capacitors are coming from, right? And these capacitors are what are called parasitic capacitances in a BJT or a bipolar junction transistor. And these capacitances are unintentional and arise from the physical structure of the transistor itself rather than being added as deliberate components. All right. And essentially the effect the transistor when we get into high frequencies, right? So before we dive into solving these capacitors or simplifying these structures, we want to understand the high frequency model of the BJT. Okay, so what I'm going to do here is I'm going to draw out a BJT cross-sectional model. So what that looks like is something like this. All right, you have, again, this is just a review, but it's also good practice. You have that this is your collector, this is your base, and this is your emitter. And let's consider an NPN. So NPN, it's going to be a plus. And here is your silicon wafer. So this is your P substrate. All right. So again, remember, N means that it's doped with electrons or negative charges. All right. P means that it's doped with positive charges. Let me change colors. All right. Or holes. And again, here again, we have E minus. All right. But essentially what happens is that between the NP channel, we create what is called a depletion region. Okay. And a depletion region here. And another depletion region here. So another way to think about this is by looking at this model that's located here. And essentially, every time you have a PN junction, there is a parasitic capacitance. So for example, in my NPN, I'm going to start at this first N. There's going to be a PN junction that looks like this. Okay, so N here and P. And whenever you have a junction, there's something called a junction capacitance or a depletion capacitance. Which is parasitic, right, in this depletion region. So in this situation, we're going to call this the parasitic capacitance at junction C or junction collector. And then again here, if you notice, there's another depletion capacitance or depletion region where, again, this is PN. So there's a parasitic capacitance at the junction of the emitter. All right. And then lastly, as we notice here, okay, the collector is connected to a P substrate, or I can also call this the P bulk. All right. And this is going to also create a junction. All right. So essentially, I'm going to have so it's going to be a little bit weird, but this is my P and this is my N. So P N. And this parasitic capacitance is referred to as the capacitance at the collector bulk. This can also be referred to as the capacitance at the collector substrate. I will use this more often than this, but they are essentially the same thing. The last capacitance or parasitic capacitance that occurs, but I won't dive too much into, is what's called a diffusion capacitance or CB. And that happens essentially in forward bias. So when you have a forward bias, or when you connect the base to the emitter, again, this is grounded, and you connect the collector to a battery source, okay, and it's in forward bias mode. So what happens is at the base, the something called base recombination, which causes what's called a diffusion capacitor, okay, and that's what we refer to as CB. This occurs because there's a rush of electrons that go into the base, and they don't have enough holes to fulfill recombination. So there's a difference in charge, right? And when there's a difference in charge in a given area, we have a parasitic capacitance. Again, that's just a high level explanation, but there is a diffusion capacitance that we need to consider. So the next thing I'm going to do to bring this full circle is draw the small signal of the BJT. Okay. C, E, and this is B. We have this as V pi, R pi. This is going to be GM, V pi. This is going to be RO. So essentially, what do we know? We know that there's a capacitance or a parasitic capacitance, C junction E, between the base and the emitter. We know that there's also another capacitance, CB, which is the diffusion capacitor. Next, there is another parasitic capacitance between the base and the collector. We call this CJC. And then we know that there's a last one between the collector and the P substrate, or CCB for collector bulk. All right. And what you will see in engineering textbooks is they refer to this capacitor here, CJC, as C mu. And these two capacitors can be joined or merged because they're in parallel, and we call this C pi. Another model or final model of this is if we have the actual common emitter representation, we then know that here is my C mu, here is my C pi, and here is my CCB. Okay, so let's go ahead now and solve the two examples, understanding full circle where these capacitors are coming from. If you have any questions or any concerns, please leave them down in the comment section below, and I'll be sure to get back to you. So we'll go ahead and look at the first example. And essentially what we want to do here is we want to answer three questions, where the first one being which capacitors can we get rid of? And what I mean by getting rid of is a capacitance that is connected to ground on both sides, we can get rid of. For this example, none is the case. The second constraint, or the second question we want to answer, is which capacitors can be merged. And again, remember, capacitors in parallel, if this is C1, this is C2, can be merged as just one capacitor, right? C1 plus C2. And again, in this situation, none can be merged. All right. And then the last question we want to answer is which capacitor experiences Miller effect, essentially experiencing Miller multiplication. All right. And in this situation, we need to look for capacitors that are connected to a voltage input on one end, or a voltage on one end and a voltage at the other end. And obviously in this situation, C mu is the case. So let's go ahead and draw out that circuit, what it looks like. So I'm going to do it step by step. So this is V out, this is RC, this is VCC, and this is V in. And essentially, we can leave the C mu, or the C pi, right? This capacitor. But this capacitor here, C mu, at my left-hand side, experiences Miller's multiplication. So it's going to look, let me just draw it over here, like this. C mu 1 minus AV. And again, this is Miller's multiplication, which was talked about in the last video. We can go ahead then and consider that we have a CCS, this capacitor. And then we also have a C mu 1 minus 1 over AV. Again, I did a video on the common emitter analysis. So from that video, we understand that AV is equals to minus GM RD. So then if we really wanted to bring this and merge all my capacitances, it will look something like this. So we have, so again, we have V out, RC, VCC, and we have V in. All right. There's a capacitor here called C pi plus C mu 1 plus GM RD. I hope that makes sense. And there's another capacitance here. We can call this CCS plus C mu 1 plus 1 over GM RD. Okay. And again, the whole point of doing this Miller's effect is to simplify the circuit so we can analyze the frequency response of the circuit in a more easier manner. So I hope that makes sense. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. So let's go ahead and go now to the second example. And in the second example, we want to answer the same three questions. So the first one is, what can we get rid of? And again, in this situation, there's no capacitor that goes from ground to ground. So here we say none. The second question is, what can be merged? And if you realize that VB, or V bias, is an AC ground, right? You can see that C mu 2, so this capacitor here, and this capacitor here can be combined because they're connected both at this node, and they're also connected to ground at the other end. So they're in parallel. So then we can merge C mu 2 plus CCS2. So what else can be merged? Again, we can notice that this capacitor here, C pi 2 and CCS1, are attached at this node and to ground. So they're also in parallel. So then we have C pi 2 plus CCS2. And then the last question that we want to realize is, which ones experience Miller effect, or Miller's multiplication? And we realize that the only capacitor that's connected to a voltage on both ends is this C mu 1. So C mu 1. So then let's go ahead and just write out the final circuit. So the final circuit. So what does it look like? So we have this cascoded amplifier. And again, I did a video on the cascoded amplifier in the past, which I'll link in the top right hand side corner. So this is V out, this is RC, this is VCC, this is biased to ground, and this is my V in. This is Q1, this is Q2. So we notice that again on the left hand side here, we have a capacitor C pi 1, so this capacitor here, plus C mu 1 minus AV. Okay. And over here at this node, we have a capacitor C pi 2, right? So again, this combination of capacitors, C pi 2 plus C CS2 plus C mu 1 minus 1 over AV. And the last capacitor we have is located here, which is going to be C mu 2 plus C CS2, again, which is this combination of capacitors. So from my cascode video, we've realized that the AV gain of this is roughly approximated to minus GM1. So this is Q1. So the transconductance GM1 times 1 plus GM2 RO2 RO1 plus RO2 in parallel with RD. In this case, it would be RC. Again, we can simplify this to just be minus GM1 times RC. And so that is essentially the final simplified circuit. And again, this makes finding the frequency response of this cascode system a lot more easier, right? And that is the purpose of the Miller effect, or the Miller multiplication technique that we've been talking about. So next, I'm going to do these two examples again for the MOSFET, right? So the common source. So for the MOSFET, right, you have your gate, your source, and your drain. So I'm going to do something like this. We're going to talk about the high frequency response or high frequency representation, right? We're going to have some parasitics located here, here, and here. So essentially the same thing we did for this video, but for the MOSFET. So please check that out or look out for that. If you like the video, please give it a thumbs up. And if you like what the YouTube channel is providing, please consider subscribing to the channel. It really helps the algorithm. Thank you.